Welcome to Operating System Week 5 Process Synchronization. This is Dr. Eliza. In this week, we will understand about process synchronization, race condition, solution to process synchronization, classical problems of synchronization. What is process synchronization? When two or more processes execute at the same time, the order may affect the execution of a process. So when more than two processes tries to execute the CPU at the same time, sometimes the data collision or the system may give improper result. So a cooperative process is the one which can affect the execution of other process. So if we have to make two processes cooperate among themselves, so synchronize a process synchronize with the other process. Suppose if two processes execute on the same data at the same time, the data may be corrupted. There are two different types of process: independent process, cooperative process. Independent process means two processes are there, executing the two processes are independent each other. It means execution of one process nowhere affecting the execution of other process. That is independent process. We no need to worry about independent process. But there is a situation where two processes need cooperation. They have some relations. So execution of one process will affect the other process. Such a process has to be cooperate among themselves. Such a process is called cooperating process. What is critical section? There is a section in the code that cannot be executed by more than one process at the same time. Such a part is called critical section. A section or a part of a code that cannot be executed by more than one process at the same time. What is the requirement of synchronization? For mutual synchronization of a process, mutual exclusion is needed. Two processes has to be mutually exclusive among themselves. Progress means if a process is not using in critical section, then it should not stop the other process. It has to give way for the other process to execute. Bounded waiting means each process must have a limited waiting time, so it should not wait for a long time. Approaches to handle critical section: preemptive is one of the approach. Non-preemptive kernels, that is very difficult to handle critical section. Preemptive means it preempts the process from the CPU, so that will help to make a process cooperate among themselves. Critical section problems: deadlock may occur, starvation may occur, overhead may occur. What is deadlock? When two or more processes are executing at the same time, if, for example, if two processes execute at the same time, both needs a resource which is held by some other process, or which is A waiting for B, B waiting for A. So there is a deadlock. So none of the process will execute. That is deadlock. Starvation means because of higher priority process execute at the CPU fast, the lower priority process has to wait for a long time, long waiting. That is starvation. Overhead: when a critical section process must acquire and release the logs, which can take time and resources. This may reduce the program's overall performance. So overhead means the acquiring resource and releasing resource. The time taken to acquire, release, that is overhead. Race condition. The race condition, undesirable situation that occurs when a device or a system attempts to perform two or more operations at the same time. The outcome of the execution depends on the order in which they are executed. So, for example, initially the value of n is 10. This is process 1 and process 2. Okay. We are assuming that the final version of common value after execution of P1 and P2 is 10. After executing P1 and P2, the value should be 10. Okay. But we may get undesired value due to lack of cooperation. That is called race condition. So the race condition may result of the following: the computer crashes, or reading error wrong data, or writing new data wrongly. These are various problems occur because of race condition. Types of race condition: critical race condition. For example, if more than two process access the account at the same time, the account is not properly synchronized by two process, the account balance will be wrong. That is a critical race conditions. Non-critical race conditions, that the non-critical race condition does not directly affect the end of the state of the system, device or program. So non-critical decision does not result in a bug, but it changes the or it decreases the performance of the system. Types of race condition: read, modify, write. These are types of race condition. This kind of race condition happens when two processes read a value in a program and write back the new value. Check then act. This race condition happens when two processes check a value on which they will take each an external action. How to identify race condition? Programmers use dynamic and static analysis tools to identify race condition. Static testing tools scan a program without running it. They produce many false reports. So how to prevent avoid shared states? So we can avoid sharing. Use process synchronization. This is the better solution for preventing race condition. We cannot avoid sharing the data or sharing the dates. So the better way is use process synchronization. Verify your learnings. A dash race condition will cause the end of the system to change. Dash race conditions, that is critical race condition, will cause the end of the state, cause the end state of the state to change. Which of the following way is used to prevent race condition in a system? To prevent race condition in a system, that is process synchronization. That only prevent the race conditions. Now we will discuss about types of solution for critical section. The problem synchronization problem, that is critical section problem, can be solved software, hardware, or programming. The software solution is Peterson solution. Hardware solution is test and set, compare and swap, and programming solution is semaphore. We will be discussing all the solution one by one. Peterson solution will have a Boolean variable flag and an integer variable turn. If the integer variable turn is equal to I, assume that we have two processes, process I and process J. If turn is equal to I, then process I is allowed to execute in its critical section. Suppose if flag of I is true, this value indicates that PI is ready to enter the critical section. So flag of I is true means that process I is ready to execute by critical section. Turn equal to I means ith process allowed to execute in critical section. And this is a solution. The left side is process PI and the right side is process PJ. See here, the PI set the flag as true, ready to execute in its critical section. And the turn equal to J, it makes jth process to enter in its critical section. Now the while loop executes indefinitely. Flag of J and turn equal to J. So J is ready to enter in its critical section and J is executing its critical section. Now this ith process will wait. If both the conditions are false, it will enter in its critical section. Once finishes its critical section, it will reset its value to false. The same thing will be written here for PJ. PJ set flag of J to true and give the turn to ith process. If flag of I and turn of I is equal to true, then it will wait for ith process. If both the conditions are false, it will enter critical section, and once finished, it set the jth flag as false, so that ith process will enter. So that only explained here. Peterson's solution, whatever I explained in this algorithm, that only explained here. So Peterson's solution Satisfy all the mutual exclusion, yes. I and J are mutually exclusive. Progress, yes. Each other allows other process to enter. Bounded waiting, yes. Each process wait for a limited time. Hardware solution. There are two hardware solutions. One is test and set, another one is compare and swap. Test and set, it uses a Boolean variable, target. If the Boolean variable is assigned to the local variable RV and the target is set as true and return TV. Here you see test and set is log. The log is true. If the log test and set log is true, then the process will wait. If it is false, when it is false, the test and set of log returns false now. Suppose the target is false. If the target is false, it will assign to RV and the false will be returned. Okay. So if this log is, this function returns true, then this system, this process will be wait. Once finish it, suppose if it is false. If it is false, it enters the critical section. Once finished its operation, it resets the log to false. That is test and set. That only explained here. Okay. The next algorithm is compare and swap. Here we have a old value, a new value, and expected value. So here, this is a old value. Second one is expected value. Third one is new. If the old value is equal to expected value, then the new value will be set as val, and the old value will be returned. Okay. If both are equal, val, the old value and expected values are compared. If both are equal, new value will set to the current value and the old value will be returned. I will explain within a program. Here you see, this is a structure here. The log value will be compared with 1. Suppose the log is 1, it returns, the log is old value will be compared with expected value. Log is equal to 0. The log is equal to 0. Log is equal to 0. There is no log. Then it performs the log equal to 0. Okay. Which of the following is a hardware solution? Hardware solution is, which of the following is a hardware solution? Peterson's solution is not. Peterson's solution, test and set, compare and assign, share and. Among these, test and set is hardware solution. One more hardware solution is compare and swap, not compare and test. How many operands are used in compare and swap algorithm? How many operands in compare and swap? 3 arguments. Old value, expected value, new value. What is semaphore? Semaphore is a variable used for synchronization of two processes. Semaphore has two operations. One is wait, another one is signal. The wait thing is, the semaphore value is less than or equal to 0, it makes the process wait. If it is greater than 0, it decrement the semaphore by 1 and execute it. Signal simply increase the semaphore value by 1. See, wait, it's an entry of a critical section. Signal is the exit of a critical section. This will act like this. There are two types of semaphore, binary semaphore and counting semaphore. Binary semaphore value will be either 0 or 1. Counting semaphore, it can have any value, positive value or negative value. So semaphore is for synchronization. That's the main advantage of semaphore. Let S be a semaphore. If the value of S is 2 at a particular time, then if the value of S is, then this is binary semaphore or counting semaphore or mutex semaphore. Counting semaphore. Answer is counting semaphore. Because binary semaphore will have either 0 or 1. Which is semaphore operation increase the value of a semaphore? Increment or wait or signal or semaphore. The signal function increase the semaphore value by 1. Okay. The signal function increases semaphore value by 1. Mutual exclusion is the property of process synchronization that states no two processes can exceed in the critical section at the same time. That is mutual exclusion. Only one process will execute in a critical section. This is firstly coined by Dijkstra. Dijkstra only coined this term mutual exclusion. So the need of mutual exclusion comes with concurrency. If two processes wants to execute at the same time concurrently, one after the another, concurrently, then mutual exclusion is needed. What is the condition of mutual exclusion? No two processes can execute in it critically. That is the condition of mutual exclusion. The term mutex first coined by Dijkstra. The term mutex is coined by Dijkstra. Now we are going to discuss about classical problems of synchronization. Classical problems of synchronization. The first problem is bounded buffer problem. Here there is a buffer with n slots. There are two processes, producer and consumer. The producer always produces the data and consumer consume the data produced by the producer. These are the two operations. Sometimes we call it as producer-consumer problem. The solution to the problem we can do by semaphore. There is a semaphore M. M is a binary semaphore used as a lock, occur and release a lock. Another semaphore MT is a counting semaphore whose initial value is the number of slots in the buffer. It will be decreased by 1 every time the slot is used by the producer. Full is another counting semaphore whose value is 0. So the full will be increased by 1 whenever the producer produces the value. Empty will be decreased by 1 whenever the consumer consumes the value. M is the binary semaphore which act as a mutex or a log between the producer and consumer. Now here you see, this is a producer problem. Producer, before entering its critical section, it is wait using empty, because empty is initially empty is empty is n. So before entering its critical section, it decreases the empty by 1. So to produce. So wait mutex act as a acquire lock. Wait perform the producer operation. When it finishes performance, mutex and it increases the full by 1 because it produces a new item. So full semaphore will be increased by 1. Empty will be decreased by 1. Initially n slots are empty. Assume that producer has produced nothing. It means all the slots are empty. It's initially empty, n slots are empty. When it produces first item or every item, it decrease the empty slot by 1 and increase the full slot by 1. Similarly, you see the consumer logic. Here, the reverse. It decrease the full by 1 and increase the empty by 1. Okay. What will be the initial value of empty? The n. N is the initial value of empty. Which type of semaphore is used to acquire a lock in producer consumer counting or binary semaphore or 0 tree semaphore are meaningless? So answer is binary semaphore. Writer reader problem. Here there are two processes. One is reader problem, another one is writer problem. The reader always read the data, writer write the data. Okay. So for writer process, we have a semaphore called a WRT. This will perform count. This write is a semaphore used for both reader and writer to make synchronization. Mutex is a semaphore for mutual exclusion of read count. Okay. Read count is a counting semaphore with increase whenever there is a read, whenever the read process reads. Okay. And here you see writer process uses the write semaphore between the reader and writer. This semaphore is act as a semaphore between synchronization semaphore between the reader and writer. For reader process, you see mutex acquire lock between the reader and writer. Mutex act as an acquire log? Read count, because it's a reader, read will be increased by 1. Suppose the reader, this if this is the first reader, if this is the first reader, it has to synchronize with writer. If it is a second reader, consecutive reader, second reader, third reader can no need to synchronize with writer. So if it is a final reader, when we decrease the read count by 1, if it is a final reader, we have to synchronize with the write process. What are the two operations that can be performed at the same time by two processes in reader-writer problem? Read and read can be performed at the same time. What will be the initial value of read count, semaphore in solution to the reader-writer problem? The initial value of read count will be 0. There is no reader. The last problem is dining philosopher problem. So there is a table in which 5 philosophers are sitting in a table. There is a chopsticks placed to their left and right. Their job is to either thinking, hungry and eating. If they feel hungry, they start eating if they are able to acquire both the forks. If they are not able to get the forks, both the forks, they have to wait. So the solution you see here, they are first checking the ith chopstick, the ith philosopher. This is the logic for ith philosopher. Ith philosopher, check the chopstick for ith chopstick. Ith chopstick is available. Then it will be checking I plus 1 mod 5 chopsticks. That is, the ith chopstick means the chopsticks in his left side. I plus 1 mod 5 means chopstick at his right. So if both the chopsticks are available, then only the philosopher is eating. Once he eat, he release the ith chopstick and I plus 1 chopsticks. So in deadlock, in dining philosopher, deadlock situation occurs because they will be waiting for another chopstick forever. Both the philosopher, when we see the diagram, see here. So if if a philosopher P3 has to eat, the philosopher needs chopstick C3 and C4. Suppose if philosopher P3 gets a chopstick C3 and waiting for C4, and P4 gets a chopstick C4 and waiting for C5, like that, if every philosopher get one chopstick and wait for another chopstick, nobody can eat. In that situation, deadlock may occur. That only given here. Which of the following is not a state of philosopher in dining philosopher problem? Eating, hungry, thinking, sleeping. Sleeping is not the state. The dining philosopher problem is deadlock free, starvation free, page fault free or fragment free. Deadlock free solution, because we are not allowing the philosopher to eat or to hold a chopstick unless they get both the chopsticks. If they get both the chopstick, then only we allow the philosopher to eat. So there is no chance of deadlock. In this week, we learned about process synchronization, race condition, solution to process synchronization, and various classical problems of synchronization. Thank you.